This is question 9-2. Students intend to use a cart spring system to study motion. A vertical plate with negligible mass is attached to a horizontal spring of spring constant K. When the spring is at its relaxed length, the plate is at position D as indicated in figure 1. A cart is glued to the plate. The cart is initially held so that the spring is compressed as shown in figure 2. The maximum force the glue can exert is F max, assume friction is negligible. The students plan to release the cart from rest so that it oscillates. They discuss whether the cart could detach from the plate during the cart's motion if the glue is not strong enough. One student makes the following claim. If the spring is stiffer, the force exerted by the spring will be greater for the same compression. This means that the cart could come loose as the spring expands before it reaches D. Right, so A and B are the usual, which one is correct, which one is incorrect. So it turns out that the first statement is correct. Okay, the Hooke's law, the force is, or the magnitude of the force, does depend on how much the spring is compressed. So that part is true. But the second statement is wrong. It says the cart could come loose as the spring expands before it reaches D. And there's no way that could happen, because at that point, the spring and the plate are both pushing in the same direction on the cart. So they're not even opposed, much less one overcome the other. So that was A and B. Now for part C, we have this velocity versus time graph. The cart's removed and the plate is coated with very strong glue. The cart rolls to the right with a positive velocity V cart, collides with and sticks to the plate, and then oscillates back and forth at the end of the spring. We've seen this before. The graph above shows the velocity of the cart as a function of time after it's completed several oscillations. Question C asks how this graph could be used along with the known mass of the cart to find the impulse exerted on the cart by the spring during the time interval between 4 and 6 seconds. So there's a couple of ways that you could do this, and here's the way I did it. They want you to find the impulse. Well, we know that the impulse, which we use J, is equal to F delta T. So I've got the delta T on the graph here, but I'd need to figure out the force. Now there is a way to do that, and I'll go over that in a second. But what I thought, well, what's impulse equal to? Well, impulse is equal to change in momentum, or M delta V. Now we know the mass of the cart, so all we need to do is find the change in velocity from 4 to 6. So you would basically take the velocity at 4, the velocity at 4 seconds minus the velocity at 2 seconds, multiply that by M. That would give me the change in momentum, which would give me the impulse. Now, mind you, they didn't ask you how to do that, because in fact they don't give you the mass, but that was my solution. So there's 2 points for this question. One point is for getting the velocities from the graph and subtracting them. And then 1 point for multiplying the mass by that change in velocity to get the change in momentum or impulse. Now you could go the F delta T way, and you can do this because you have a velocity versus time graph, which means you could get the acceleration. So you could get the acceleration from the slope of the graph. Now you have to be specific because we wanted the slope of the graph between t equals 4 and t equals 6. But you could do that. Then you could get the F by multiplying M times A. And then you could get the impulse by multiplying that force by delta T. So let's see, the 2 points there were 1 for indicating that F delta T gives the impulse, and then 2 for getting the acceleration from the graph, multiplying it by the mass to get the average force. All right, so that's A, B, and C. So now we'll get on to the paragraph part. And the paragraph part says the collision's repeated with a lighter cart. Everything else happens the same. In a clear, coherent paragraph length response, explain how the graph of the car's velocity as a function of time would differ from the one shown above if the cart were lighter, and provide a physical reason why each difference would occur. Okay, so if the cart were lighter, the period would change. Okay, the period is 2 pi m over k. So if m decreases, then the period would be shorter. Okay. Also, with a lower mass, the car would have less kinetic energy and therefore compress the spring less. And so the amplitude would be, of the oscillation would be smaller. However, the maximum velocities would be the same. So the amplitude of this graph wouldn't actually change. So in this paragraph, there are 6 possible points. One for saying that the period would change, just change. You don't have to get shorter, just that the period would change because of the mass of the cart. Then 1 point for saying the period is shorter because the mass is less. 1 for saying that the amplitude of the velocity wouldn't change. Or if you say nothing else would change, you can have that point, and you've got 3 points so far. Then you could get a point if you could justify why the maximum velocity wouldn't change. Then they say an additional point for any additional correct statement, even if it's not related to the graph. Here's another one that I think is kind of bogus because they didn't ask you for this. However, if you mentioned that the frequency would increase because the period is decreasing, if you measured that the energy would decrease because it won't compress the spring as much, if you mentioned that the spring would compress less, or if you mentioned that the maximum acceleration would change, any of those things, you could have an extra point for saying that. And then 1 point for a clear, coherent paragraph. So 6 points for the paragraph portion of this.